Okay, so let's talk about the torque a little more. We'll do an example. Suppose we have a meter stick, and we're going to kind of ignore the thickness of the meter stick. So it's just kind of like a long, thin rod, 1 meter in length. And suppose we apply some various forces. Maybe we have a force one point at one edge pointing at a certain angle, and maybe right in the middle we have another force, and then over on this side we have a third force, and maybe that's probably good. So we'll call them F1, F2, and F3. And you know, the torque is a funny thing because we cannot really say the net torque on an object until we know where the axis of rotation is. Because for a meter stick, I mean, it could rotate about the center, but we could also sort of clamp down one end or put a pivot, a pin or something on one end. So in this case, we're going to say maybe that it's pivoting about the center. So the pivot is right in the middle, okay? And we want to find the net torque. So if we have forces of maybe, let's say 20 newtons, 30 newtons, and 25 newtons, and angles of 40 degrees and 20 degrees. Okay, so those are all the information we need. And I'd like to know which way this thing's going to rotate. So that is, there's multiple torques and they're kind of fighting each other a little bit. And we cannot answer yet what the acceleration is because we don't know how to find I, the moment of inertia. Remember that net torque equals I alpha. We don't know how to find that thing yet, okay? And we, in fact, will not learn how to find it today. So I'm really just used as an example of finding torques and adding them up. And we're just going to basically see, you know, once we have a final number, does it indicate that it's going to rotate clockwise or counterclockwise? So for the signs of torque, or the sign of torque, okay, it's plus sign for counterclockwise, and it's a minus sign for clockwise, indicating that if the torque is, if the force is trying to make the object go counterclockwise, you get a plus sign. If it's trying to make it go clockwise, you get a minus sign. So that sounds a little backwards, but just remember that when we do angles in math class, our angles always go counterclockwise. The counterclockwise direction, positive direction for angles. So that's kind of what we're using. So when we're adding up the torques, if we get a positive number at the end, it means this thing will rotate counterclockwise. If we get a negative number at the end, it will mean it's going to rotate clockwise. And if we get 0 in the end, it means it doesn't rotate. So we're just going to compute the different torques and then add them up. So torque 1 would be what we would call R1 times F1 times sine of theta 1. So in my picture, I can draw R1. So what is R1? It's from the pivot point to force 1. So it stretches like that. I should use a lowercase r, R1. R3 Looks like that. But R2 is very difficult for me to draw. If I draw it, this is what you see. Did you see that? Anyone catch me draw? I think it's very hard on the digital medium to see it. But always I just tapped my pen right at that spot. In other words, we cannot draw R2. So we'll deal with that when we get there. For R1, remember I said that this is a meter stick. So R1 is just 0.5 meters, half of the length of the meter stick. And F1 is 20. I'm going to leave room for us to decide the sign in a minute. 20 newtons. And then we have the sign of the angle. So that's the angle between R1 and F1. Technically, that angle would be 140 degrees. However, it's an interesting fact about sine that the sine of 140 and sine of 40, as long as any two angles add up to 180, their sines will be the same. So it always is the case when we're doing torque that it does not matter if I use this exterior angle or interior angle, whichever one is more convenient. So I'll just use the 40 degrees. Now we have to ask ourselves, does force 1 make this thing want to rotate clockwise or counterclockwise? I'm going to give you a little poll. So think about it for a minute. Clockwise or counterclockwise? Force 1, keeping in mind that this thing is pivoted at its center, what does force 1 make the meter stick want to do? You want to go clockwise or counterclockwise? Okay. There are our responses. Okay. So which way, first of all, which way is clockwise? Clockwise is that way. And, counterclockwise is that way. So if it's unclear to you when you're looking at a picture, the answer is clockwise. Okay, it's clockwise. We got 4 votes here and 4 votes there. It's clockwise. If it's unclear to you when you look at this, what you can do is the following. Okay, so you can take your pencil and hold it like the meter stick. And then, so I don't know if I'm mirrored or not. I don't know if I'm mirrored. I'm pushing on the left side of my pencil, and I'm putting the direction that F1 is going. So when I do that, from my perspective, so try it with your own pencil. From my perspective, I see a clockwise rotation of my pencil. So anytime it's unclear, you can hold your pencil and you can push it in the same direction, holding it in the same place where the pivot is. If the pivot's on the right edge, I hold the edge. If the pivot's in the center, I hold it in the center. Okay, so try that out. See if that helps you to see that it should be clockwise. Okay, any questions about that? I'm not sure why we were split so evenly on. Cody.
So does it matter if the answer for the torque is a positive number? I think that's partially why I chose counterclockwise.
Do you mean what I wrote here on the equation?
Yep.
Yeah, it matters, but I'm not done with the equation yet. So
Okay.
I have to either put a plus sign here or a minus sign. But yeah,
Okay.
yeah, okay. So thank you for clarifying that. So I wasn't done with the equation. So I was actually trying to fill in the equation. So because it's clockwise, we should get a minus sign there. Okay? Raise your hand if that's kind of what you were thinking, that you picked counterclockwise because I had a positive thing here. Okay, awesome. So that clarifies that. Now, but keep in mind, anytime you have trouble thinking, is it clockwise or counterclockwise, actually take your pencil or some physical object and kind of hold it and push it in the way indicated, and that should help you see what's going to happen. Okay, so when we're finding the torque, it's actually really easy because it's always the same. It's R times F times sine of theta. Usually finding R and F is easy. Finding the angle, it should be somehow given in the picture, but it's the sign that we have to still think about. Is it going to be clockwise or counterclockwise? We cannot assume. So in this particular case, though, we can get a number for it. So negative 0.5 times 20 times the sine of 40 is negative 6.43 Newton meters. Notice the units of torque are the same as the units of energy, Newton meters, but we do not call them joules because there's no work until this thing starts to rotate. Okay, so we just call them Newton meters or foot-pounds in the English units. And it's got that minus sign. So what we're going to do is we're going to find the torque produced by force 2 and force 3. When we add them all together, if the total number is a negative number, it means it's going to go clockwise. And if it's a positive number, it's going to go counterclockwise. Okay, so that's torque 1. Danielle.
Just to clarify, it's negative because it's the clockwise, right?
Yes, that's right.
Okay.
Sure. And again, kind of tacking on to what Cody said, there's really no way from the equation for us to know ahead of time if it's going to be positive or negative. That's going to come from the picture. So we still have to be good at drawing force vectors and getting them in the right place at the right angles. Okay, now we do torque 2. That's going to be R2, F2, sine of theta 2. Well, I know F2, but I cannot find theta 2 because I cannot draw R, and I cannot really see R2 because it's so small. In other words, R2 is 0. And because of that, I just know that force 2 produces no torque. If we look at force 2 and we ask ourselves, does it make this thing want to go clockwise or counterclockwise? Just think for a minute about if I just showed you this picture and said, does force 2 make the meter stick go clockwise or counterclockwise? Raise your hand if you would find that confusing. If just a question that would be confusing. Okay. It should be confusing because it doesn't produce torque. And whenever you're in a problem and you get to a force and you ask yourself, let's see, is that going to make it clockwise or counterclockwise? If it is not clear, that is a very, very strong hint that that thing produces no torque. Okay, so that's just something to think about. Why does it produce no torque? It's because the R is 0 in this case. Then we can go to torque 3. That's going to be R3, F3 times the sine of theta 3. And the R3 is also going to be 0.5 meters because it's also located halfway from the center. The F3 is 30 newtons, and you have the sine of 20 degrees. and I get 0.5. What's that? Sorry, 5.13. We still should think about the sign. Should this one be clockwise or counterclockwise? Let's do a new poll. So that is plus or minus. Hold on one second. I'm going to try to put a poll up. Okay, we have 7 counterclockwise and 1 no response. So counterclockwise gets a plus sign. So I actually like to write the plus sign, even though from a math standpoint you don't need to write the plus sign. I like to write it down because it just lets me know that it's positive, and it's positive on purpose and not on accident because I forgot to think about the sign. So I like to write it down just to kind of be sure. Now we can say, what's the net torque? So we're going to have minus 6.43 plus 0 plus 5.13. That looks like negative 1.3 Newton meters. So which way will this thing rotate? You can type it in the chat or say it out loud. Which way is this going to rotate? Ziad?
Clockwise?
Yes, clockwise. Now, how fast is it going to go? That I cannot answer without knowing what the moment of inertia is. And we're not even going to learn that really in this chapter, okay? So we're really focusing on the left-hand side of this equation. Any questions about any of the 3 torques? Okay, I'm going to give you a little exercise to do, just to quiz you. So suppose we have a force pointing like that. So let's call it force 4, and it's equal to 40 newtons. Go ahead on your own, find the torque 4. Try to work that out on your own, and I'll do it in a minute. Okay, does anyone have an answer yet? So the formula for torque 4 is going to be R4 F4 sine of theta 4. And then we need to know if it's plus or minus, clockwise or counterclockwise. Let's start with that, the clockwise versus counterclockwise. Oops, I think I took my whiteboard off instead of adding a poll. Okay, who says it's clockwise? Who says it's counterclockwise? Let me update this a little bit. Okay. So I'm adding a question mark. Okay, so we have 7 confused and 1 no response. We had 3 clockwise when I didn't give a I don't know or confused. So if you're confused about which direction, that is a good indicator there's no torque. Why is there no torque? Well, we are going to have 0.5 times 40 times the sine. What's the angle? Well, the way to see the angle would be if we make axes and we draw them on coming from the same origin. We can see that the angle is 180 degrees because one points to the right and the other points to the left. But even if you call the angle 0 degrees, it doesn't matter. Sine of 180 and sine of 0 are both 0. So you're getting 0 torque out of force 4. So did anyone get 0 when you were doing this? Raise your hand if you got 0. Okay, raise your hand if you couldn't get it because you were confused about the angle. Okay, that's reasonable. So whenever they're in a line together, A, it's confusing which way it would make it rotate, and B, that confusion is a good sign that there's no torque. You need at least a component of this force to be perpendicular to R. And if it points against R or with R, suppose on this side I had a force that's just going in the same direction as R, that would be a 0 degree angle. It would also create no torque. Okay, so those are the cases that are going to be sometimes a little tricky, but once we learn how to recognize them, they're actually our favorite cases because we can just cross that torque out from the beginning. Okay, let's do a problem where we finally get to see what we do with torque. Oops, that's not what I wanted to do. Okay, so suppose we have a building and we want to put a sign on the building. So what we do is we put kind of a, I don't like that. We put a rod, like a pole of some sort, sticking out of the side. Getting a lot of lag on my software again. Okay, so we've got this sign, and there's a rod. Okay, there it is. I've got this sign, and the sign says, "Eat here." You guys remember restaurants? Raise your hand if you remember restaurants. Almost everybody. I'm getting where I don't really remember them, but okay. So you want to make this sign, and if you don't prop it up somehow, it's going to fall down. So you connect a chain or rope at the far end of the sign. And what I want to know, the question I want to answer is how big will the tension in that rope be? So if we would draw the tension as a red arrow, you know, there's tension there. I want to know how big it has to be. If the mass of the sign, let's say the mass equals 50 kilograms, and maybe the length of the sign is 4 meters. That's kind of big. Maybe 2 meters. And the angle here, let's call that 50 degrees. Okay? So I want to find the tension. This is a static equilibrium problem. We did static equilibrium problems before where we had like a mountain climber hanging from a couple ropes or something along those lines. So this is like that, but a little different. Let's see why. So to do a static equilibrium problem, I have to draw all the forces. So the force of gravity, I would put that right in the center of the sign. Usually when I'm reading a problem, the problem will say something like a uniform sign. Uniform means the force of gravity is located right in the middle. Now, we never cared about where the force of gravity was or where the tension was or where the friction was before because we didn't worry about the size and shape of our object. But once we start talking about torque, it's very important that we know where the force is acting, okay, because that influences the value for R. So those are the two forces so far. How many forces should I have on this whole thing? I don't know how do we decide how many forces? See that?
You look at the points of contact, and then it should be one more for the
Yeah,
torque.
so how many points of contact do we have?
I think 2, right? Because you have the sign and then the chain.
Yeah, exactly. I'm thinking kind of the rod and sign as just one unit. It's connected on the right-hand edge where the rope is, and it's also connected to the wall on the left-hand edge. So there's 2 points of contact. There should be 3 forces. And so this third force, I'm just gonna draw something and call it force of contact. Maybe I'll call it force W, the force from the wall acting on the sign. But the problem is I don't really know how to draw that. I know there must be some kind of force somewhere. You know, presumably there's some bolts or something connecting this thing to the wall. And I don't really know how to draw that force. So let's see if we wanted to solve this for tension, how would we do it? We have 3 forces. We would say net force equals MA. But we'd say, well, our goal is that the sign doesn't accelerate. We want to have a strong enough rope that it doesn't fall down. And so we split this into X and Y directions. And then in the X direction, we're going to say F wall X minus TX equals 0. In the Y direction, I have F wall Y plus TY minus force of gravity equals 0. Never mind that I don't know if I drew F wall correctly. Okay, I'm leaving totally open the possibility that it's not, that drawing is not correct. Maybe F wall points straight up, maybe it points to the left a little bit. I don't know. Okay, so I need it somehow, but the sign of it could be different. And then let's see what we know and what we don't know. We know the force of gravity, basically, because we have the mass. But we don't know Tx or Ty or F wall X or F wall Y. So we have two equations, but we have four unknowns. So we know that we cannot solve, two equations with more than two unknowns. We have four unknowns. So we have to try to keep working, and trigonometry will help us a little bit because Tx would be T cosine of theta, and Ty would be T sine of theta. And we know the theta too, right? So we know theta, mg, and now we only have three unknowns. Now, if we try to do the same business with the force of the wall x and y, calling it cosine of theta and sine of theta, it will be a different theta. And we don't know that angle. That's the problem. We don't know this angle. If we knew the angle, that would be okay. That would then look like a mountain climber hanging from a couple ropes kind of problem. But we don't know the angle. So it won't help us to put sine of some unknown angle and sine of some unknown angle and cosine of that same angle. So we really need a third equation. And that's where torque comes in. Because not only does this sign not move up or down, which tells me AY equals 0, or left or right, which tells me AX is 0, it also should not rotate. So that tells me alpha equals 0. So we're going to have a torque wall, a torque tension, and torque gravity, which somehow combine to give me 0. But I cannot figure out the signs of these things until I know where the pivot point is. Now, in this problem, the pivot point was given, but this problem never said anything about a pivot point because this thing actually doesn't pivot, right? That's what we're saying. We don't want it to rotate. So what is it not rotating about? Well, it's kind of ambiguous. Maybe we do the same thing and we say it does not rotate about center. Because that's true. That's a true statement. It doesn't rotate about the center. Or maybe we say it doesn't rotate about the corner where the rope is attached. That's also a true statement. We could say it doesn't rotate about the left edge. That also has to be true. We could say it doesn't rotate about this point up in space up there. That's also true. The point is, it's not rotating about any point at all. So that, rather than being a problem, that is the best news we could have. Because it means we are free to pick any point we want and let that be our pivot point. This only happens for equilibrium, when something's not rotating. If it's actually rotating about a pivot point, then that's the pivot point. We don't have flexibility there. But if it doesn't rotate about every single point in the universe. So we can pick any point we want and say it doesn't rotate about that point. And I would say that those 3 points I listed are all really nice candidates for where to choose the pivot point. Okay, but it is a choice. Where do we put the pivot point? If I choose the center, then I will be able to cross out the torque produced by gravity because that's the case where the force is located at the pivot point. Just like in our previous example, this force 2 gave no torque because it was located at the pivot point, and so its R value was 0. In this case, if I pick the center, then the torque produced by gravity, I can just cross it out because the R would be 0. Or maybe I use the right edge and I can eliminate the torque produced by tension. That's a valid choice also, and it definitely simplifies my problem and gives me only 2 torques instead of 3. Or finally, I could put the pivot point on the left, and then I could get rid of the torque from the wall. Now, they would all be good choices, but one of them is the best choice. One of those choices is better than the other 2 because it gets rid of sort of what we would like to get rid of. It gets rid of the most problematic forces, most problematic of our torques. So I'm going to give you a poll. We're going to vote. Do this democratically. Okay, and see which place we would like to place the pivot point. The left edge, the right edge, or the center. So go ahead and just pick what you think would be the best. And then we'll decide. Okay, so we had left, left, right, and center. And we had 5, 2, and 1 votes respectively. So most people like the left edge. Someone picked the left. Tell me why you picked the left edge. Nobody knows why? Ziad.
I was thinking about how we had an issue when we were using the sum of forces formula in the top right there.
And what was our issue?
Oh, I totally forgot. I think we just didn't know the angle, I think. We didn't know the direction, so we weren't able to really do anything with it.
Yeah, exactly. So here's the idea. We can always get rid of one of these torques, but we want to get rid of the most problematic one, the one causing us the most problem. That's kind of like when you're on the contest and you get to scratch out, 2 out of 10 problems. You don't get rid of the easy problem, you get rid of the hard problem, right? The one that you're not sure it's right. So we want to get rid of the force from the wall. That's the best choice, but any of them would work. So let's let me get rid of those dots. And we're going to pick as our pivot point, our sole pivot point, the left edge. So when I do that, not only can I cross out the torque from the wall, okay, for the reason we said, that its radius is 0, but now I can figure out the signs of the other torques. I cannot figure out the signs until I have chosen the pivot point. Okay, so for the tension, the torque, there's a lot of T's here, aren't there? There's the torque looks like a T, but the tension is an actual T. So the torque from tension, that is making the rod want to go that way. Okay, it wants to go that way, which we would call that counterclockwise. So torque from tension is going to get a plus sign. And the force of gravity, it's trying to make the sign go this way, around that pivot point. So it gets a minus sign. The signs of these depends on the pivot point I choose. If I had chosen the right edge, then the force of gravity would be making it want to go that way, which would be counterclockwise. So the sign depends on the pivot point I choose. Now, once I've clarified this, I have the torque from tension equals the torque from gravity, and we can write out our formula. That's going to be R tension times sine of theta tension equals RG FG sine of theta G. And we want to solve for the tension. So we just do a little bit of algebra. And what's really cool about these problems is they basically all, got a weird little squiggle there. They all work the same way. We write down some of the torques, we choose a pivot point, we cross out one of the torques, we write out the formula for each one, and then the algebra always looks very similar. So normally what I do when I've got all these symbols, this one is a pretty easy problem, but for harder problems this becomes more useful. I like to make a table and just all the things I need to know. I need to know RG, I need to know FG, I need to know theta G, and RT, and theta T. Okay, so RG, let's draw out what that is going to look like. It's going to be a line going from the pivot point to the location of the force of gravity. So right there, that's my RG. That is exactly half of the length. So that would be, since my length is 2, that's going to be 1 meter. The force of gravity is 50 times 9.8, m times g. The theta for gravity, we have a right angle there. So that's going to be 90 degrees. Remember, it's between R and F. The R for the tension is just the length, which is 2 meters. And the theta for tension is 50 degrees. So once I fill in the table, again, this problem's pretty easy, but for harder problems where there's more torques, there's so many different symbols that it's a good strategy. We're going to have 1 meter times 50 times 9.8 times the sine of 90 over 2 meters times the sine of 50. So let's see what we get. I get 300 and about 320 newtons. Okay, let me kind of recap. I really want this example to make an extreme point. So before we knew about torque, we could have seen this problem. I could have offered this for extra credit, and some of you probably would spend hours and hours trying to figure it out, and you would get nowhere because we only have 2 equations and there's 3 unknowns. So once we realize we need another equation, we have the torque equation. Net torque equals 0, just like net force equals 0. But it turns out, that the torque equation, rather than being the 3rd equation in a 3 equations, 3 unknowns kind of situation, turned out to be just a sufficient equation on its own to find, sorry about this, I didn't try to move that. Okay, it turns out to be a sufficient equation on its own to find the tension. So what looked like an impossible problem, 2 equations with 3 unknowns, and then looked like it would be a hard problem, 3 equations with 3 unknowns, turns out to be a very easy problem because torque is very powerful. The fact that it allows us to eliminate one of our unknowns, and this is always something we can do. We can always choose a pivot point to get rid of the worst unknown. Oftentimes then, we can solve for what we're looking for using only torque. Now, once we know the torque, if we wanted to find F wall X and F wall Y, we could easily find them. Let's just go ahead and do that. F wall X would then be T times the cosine of theta, which is going to be 320 times the cosine of 50 degrees That's 205. Well, let's round it to 206. 206 newtons. And the F wall Y would be mg minus t sine of theta. So that's going to be 490 minus 320 times sine of 50. So I'm running out of room, and my lag on my screen's getting super bad. So I apologize for how that looks. 490 minus 320 times the cosine of 50. Okay, so that's 284. 284 newtons. So it looks like my drawing was actually about okay where I put the F wall. It definitely points in the first quadrant because the X component and Y components of that force are both positive. And if it pointed in a different quadrant, this would tell me that. But keep in mind, I never used that fact to find the tension. We could even find the angle for the F wall, call that theta wall. And that would be just the inverse tangent of the F wall Y over F wall X. So that's 284 over 206. Hold on, that's not the right number. I used, because this got so messy, I used a cosine instead of a sine. So that's actually, this should have been 245. And I get 50 degrees. So it turns out that the force from the wall points at the same angle as the tension, and that's because of a certain symmetry there. In fact, if we find the magnitude of the force from the wall, which is going to be, using the Pythagorean theorem, the square root of 206 squared plus 245 squared, we will get 320 newtons for that also. Okay, so that's the basic idea. What we will be doing going forward. Tomorrow, we're just going to have a boatload of problems to practice that are along these lines. But they all work the same way. You draw the picture, you draw in the forces, you choose a pivot point in such a way as to get rid of the worst force possible, and then you use net torque equals 0. That is often enough for you to find your unknown, but if you need them, you can also use net force equals 0 for X and Y components. For example, if we want to find the angle and magnitude of this force wall, we would have to go back to Newton's second law for linear equations, the Latin version. But between the two of them, between net force equals 0 and net torque equals 0, we can solve absolutely any static equilibrium problem. So tomorrow, we're just going to do a lot of practice of all types. Some of them will be human body related, like how much torque how much force your body needs to exert to do an arm curl, or to do a push-up. What kind of forces are necessary in each arm? Things like that relate to the human body, as well as things that relate to construction. I know some people in this class are doing construction management, and so some of the examples will be relevant to, building bridges and building, structures, because the one thing you don't want to happen when you build something is for it to tip over, to fall down, and that's all about getting the torques to balance as well as getting the forces to balance. Okay, so any questions about this example? All right, you can go ahead and try some of these homework problems, but if you may, if you're feeling like you're not sure how to do it, then just wait for tomorrow. After we get a lot more examples, it should be pretty clear how to do all of these problems. Okay, so that's it for today. I will see you tomorrow. If you have questions, stick around. Otherwise, thanks for showing up.